back to this now. The set of equation was that there, and I went ahead and put this on the board. Tangent angle A, okay, is equal to A over B. And if we put the numbers in here, tangent angle A is equal to 3 feet 2.5 inches divided by 7 feet 6 3/4 inches. If you look on page 228, now we calculated the first time, we calculated the long way, where we took 2.5 inches divided by 12 and all that. It's the long way. I said there was a short way. Well, come to find out that a civil engineer named Constantine Smoley, before we had calculators and before we had you know, computers on our desk and all of that, he went through and he calculated hundreds and hundreds and thousands of charts for calculations. He did this and he created a book. It was basically a Bible for engineers and architects on all of these charts. And one of the charts he did was a decimal foot chart, which is in your book. And believe it or not, this today is still used by a lot of people because it's just easy and fast to find something. You look across the top of the chart there, it has inches, and on the right side there, or left side I should say, it has the fractions of an inch. All right. So if I was looking for 2.5 inches here, I'd go down the 2-inch side, 2 inches across the top, look for the ½ inch, and there it is, 0.2083, and that's exactly what I have on the board here. 6 3/4, I'm going to look on the 6 across the top, come down to 3/4, and that's 0.5625, and that's what we have here. So it's a very, very fast and easy and accurate way to calculate instead of dividing by 12 and going through that. Now, if you had a lot of these to do, okay, if you had a lot of calculations that you had to convert to decimal feet, the best way to do it would be set up an Excel spreadsheet. Okay, do the calculation so anytime you typed it in, it would automatically give you the decimal feet. If you're doing one-offs like these here, again, this chart's my best friend. Okay. So I did that, and the reason why I wanted to do this one on the board, because when we did the math here, okay, tangent A of the angle is equal to 3.2083 divided by 7.5625. We get tangent angle A is equal to 0.4242. What do you do then? Anybody know what to do then?
Inverse tangent.
The inverse tangent. Thank you. The inverse tangent, well, what it'll do is take this, the inverse tangent here, and we'll get A separate now. So we're looking for the angle. And what happens when you do the inverse tangent of 0.4242? You actually get 22 point something.
9.
0.9 it is?
Yeah.
22.9 degrees. Now you can convert the 0.9 degrees into minutes, but we don't need to go that far. So what we've done, since we needed that angle there, angle A, we were able to calculate that by just using trig. And this is great. Now we can figure out an angle, any angle that comes up. If we wanted to, and I'm not going to do this for time's sake, if I needed this dimension C, okay, again, back to the Pythagorean theorem, A squared equals B squared plus C squared. We have the A and the B, we can calculate the C with the exact same calculation we just did earlier. So we don't have to go into that again for time's sake, because the next phase I really want to talk about is compound angles. What happens now when we have something really strange going on, and this happens a lot. I'll say this happens a lot. Where we have this pipe coming in, it's coming up at this angle from here across the diagonal of the room and then back out the top. So basically if we looked at this room here, okay, my pipe comes in down here at that corner and goes all the way over to that corner over there. Alright, and goes out the wall. Now that's a little different. Now we have to figure out how we're going to calculate this travel here. Now, before we go any further, let's talk about some terminology. When we're talking about compound angles and calculating compound angles, it's the same calculations we just went over. Okay, but we have some terminology here. And we'll look here, we have run, okay, which is this imaginary box that we put around this piping. This imaginary box can be any size. It starts from where the pipe comes in and bends, where the pipe goes out and bends. Okay? And it can be, we can put that imaginary box on anywhere. We have the run, which is the length of the total offset in the direction of the pipe run. We have the set, which is the height. We have the roll, which is the breadth or the thickness. And what we're trying to find out, calculate, is this travel, which is this length of pipe. Okay? Believe it or not, this may look difficult, but it's not. It's how to break it down into separate components to calculate it.
I just got a small question in regards to the three names there.
Mm-hmm.
Are those like associated with a certain axis of perspective? Because like say if you took that whole picture there and rotated it, now does that mean the roll is a different measurement or it comes with it? You see what I'm saying?
It would go with it.
Okay.
Yeah. These are more or less to give you an idea of where we're talking about when we're talking about run, roll, set, and travel. You're basically trying to figure out what this travel is. Okay. Now, if you look at the screen, to do this, we need to use the same Pythagorean theorem we just talked about and calculated. But how would we do that? How would we figure this out? All right, this is where you really got to look at this, analyze it, and visualize how we can do this.
You take it.
Go ahead.
Oh. Basically, you look at it as two triangles, from above and also from the side.
Right.
And, well, I should say, if you solve from above, you can figure out using the run and the roll there. You can figure out. Let me see. Let's just say that the run is the x-axis, right? So if you're looking down at it, you can figure out the angle of a bird's eye perspective, right?
Right. Right.
You can then use that to kind of get a skewed. I wonder if I should try and illustrate what I'm trying to say, because.
Sure.
Okay.
Want to come up? Yeah.
Let me just try and sketch it and make it a little clearer.
Here's a couple different colors.
Oh, just one.
Okay.
So let's say, just for argument's sake, here's our cube of space. We've got this pipe going from here to here.
Right.
Well, from this point of view, it looks something like this. Now we can use this top view and these two measurements to figure out this angle. Then we can use this measurement to figure out a triangle that looks something like this here.
Exactly. Yep. Exactly. You're breaking it down into separate components. Right. Now, it also, this is very important. It's because each of us is going to look at it a little differently. Okay? Is his way of doing it wrong? Any ideas? Okay? He's looking at, first of all, looking at this triangle here. Okay? All right? And getting what dimension? He's getting this one down here. Once he gets that one, he has, okay, the B dimension, he's got the A dimension, he's looking for the total C. So he looked at it, okay. Another way to look at it, which is, again, perfectly right, I can do it this way. And what I'm doing here is I'm taking this triangle here, okay, which would then look at it, I get this triangle too, okay. He's calculating it from the bottom view here to create this triangle. And I'm looking at it at a different perspective and giving you this other triangle, which is correct. Both are correct. If you calculate them both out the same way, you're going to get the exact same answer. So depending on how you visualize things, okay, Kevin, your calculations may be different than mine. They're both going to end up at the exact same calculation that we're looking for. So that was good. That was very good. Again, here we are using the Pythagorean theorem. We had that triangle A. We had the dimensions already that were for triangle A. Let me bounce back and show you that, which was the this triangle here, which was the roll and the set, which we have. And we put them into the Pythagorean theorem. We come out with this C is equal, which is this line here, 2.7742. We take that number, and now that we have this here, we have this length here, we can now figure out this next triangle. And here we go. We put that number in at 2.7742 into the calculation. We have the B dimension. We can go through the math again, which we've already proved we could do that earlier. Looking at Smoley's chart again, we can get to the closest 16th. We can work it backwards. That chart goes both ways, frontwards and backwards. If you have the decimal foot, we can look and see what the actual inches will be. So our total travel here, without doing the math manually, is 4 feet 9 and 1/16 inches. Again, something that was easy to do. That we've done this already a couple times. So we've taken this compound angle here, and we figured out this travel by just doing the calculation of the Pythagorean theorem. We could take it a step further and actually calculate these angles in here if we wanted to. Okay, but for time's sake tonight we're not going to do that. One last thing, a very, very helpful chart in your book that I really want you to take a look at is on page 227. First of all, we have the Pythagorean theorem in front. On the top here, it gives you everything you need. If you're looking for A or B or C, the calculation used. Be very careful if you're solving for B, that it's C squared minus A squared, and not just, like if you're looking for C, it's A squared plus B squared. Be very careful that you're using the right symbols in there to do the right transaction. Another nice part about this chart, if we have two sides here and we're looking for either angle A or B or C, it gives us if it's going to be a tangent, sine, or cosine. Okay, so then again, this chart really helps you if you have some of the information, what equation to use to get the final equation. Okay. Again, one of these charts are sometimes priceless, especially when you get out in the workforce and you've got to do this stuff, and you're thinking, oh yeah, I remember doing that in class. Where was that? Oh yeah, it was in that chart. Okay, so you can then go back to this chart, reference this chart a lot. And it gives you some other things in here to how to find different angles. Also gives you a nice little area here. If you're trying to find the area of a triangle or area. So that's just an extra chart on there that's in your book that you're going to use a lot. Now that's it for the presentation portion. The homework you'll do on this will reinforce everything we've gone through. You can reference your book. The presentation that I've just done here is going to be on angels. You can look at that later if you need to reference back to that. And again, if there's any questions along the way, you can always email me through Angel, and I can get back to you. Any questions as we go further? Okay, so we recap what we've done tonight. We've looked at Pythagorean theorem. We've looked at the Pythagorean theorem to find the length of a line that you're missing. We've also looked at trigonometry and how to figure out the angle that you're missing, the unknown angle. We'll do that now. Biggest point, I'm glad Kevin, you came up here and did that, the visualization of compound angles. That is probably the trickiest thing that you're going to have to go forward on, especially in the homework, is visualizing where it is. I gave you some easy ones to visualize. Once the skewed angle comes in and it's a little difficult to see, that's when you're going to really have to think about and visualize in your head what your angles you're trying to find. Okay, what triangles you're trying to find in your head. Any questions? No? All right, thank you. That's it for tonight.